So we'll have the coffee break after a couple of talks. There was some confusion from our side, but coffee break is scheduled at 4:15, and we meant this to be a transition time so that you come back from your mentor sessions. All right. So in interest of time, let's get started. Our first speaker for the afternoon is Professor Auroop Ratan Ganguly. Auroop and I go a long way, by the way. He was my advisor during PhD. So Auroop is a fellow of American Society of Civil Engineers and PhD from MIT with 24 years of full-time professional experience in the US, spanning the private industry, government research laboratory, and academia. When I asked him today that what he considers his most important accomplishment so far, he said it was opportunity to be former PhD advisor of Udit Bhatia. So let's hear from Auroop. And he asked me that I should read this aloud. So I have done that. Now over to you, Auroop.
Can you hear me? All of you? Okay. So yes, indeed, it's a pleasure to come here and to be able to learn from Udit. By the way, I meant every word that I said. Although to caveat that, I say that to all my PhD students. All right. One thing here, the presentation that I'm going to give here is going to be maybe slightly different from the kind of presentations you have been hearing so far. Udit has been saying to me that I've grown very light over the years. As I've grown very light. There are no equations on my slides. So I apologize for not having equations on my slide. But to my defense, I would quote Aristotle and say, there is no royal road to learning. You have to read those papers. For the equations, please read those papers. I'm just kidding, by the way. It's fine to have equations in presentations as well. But what I can do here is give you a sense of the broad nature of the problem, which sometimes we miss. We solve these individual details and which needs to be solved so much, we stop thinking about the broad problem. I will allude to our papers, presentations, both in computer science and in this case, climate science and infrastructural engineering and some interdisciplinary venues. So I'll allude to those, but I'll not go into as much details for those. I request you to please read those papers, and then I'll be happy to discuss with you. Okay, so in the interest of time, first of all, I am at Northeastern University in Boston, and I am also a research scientist. I'm a chief scientist at US Department of Energy's Pacific Northwest National Lab. And here are the funding agencies whom I should acknowledge. So I have just listed them here, or at least the major funding agencies. If you're interested, I request you to visit my lab. Almost all the work that we do as faculty. So I have been in the, like Udit was kind enough to say, I've been in the private industry, I've been in government lab, but especially in academia, all the work that you seem to do is really the work of our students and postdocs like Udit, and we just come and present. So for that, please visit my lab. It's sdslab.io to get more information. All right, with that. So first I'll talk about climate resilience and data science. Now, when I say climate resilience, there are various aspects to that. Some of us, when we think about climate, we think about greenhouse gas emissions and what that does to the environment, and that's an important aspect of climate. But when you think about climate resilience, we also talk about, okay, you know, and right now I'm coming from Kolkata, so every monsoon the city floods. And people ask me, okay, climate change, something needs to be done. We need to reduce our greenhouse gases. And I say, well, reduction of greenhouse gases will not necessarily stop the floods in Kolkata. You'll have to do something with infrastructures. You have to do something with urban planning. So all of this, when we say climate resilience, we talk about all of these things combined, and it's important to understand that. And one thing I'll talk about here is where and how can data science and artificial intelligence, especially a broad definition of artificial intelligence, where can that contribute? As you'll see as I progress through this, I'm less interested in the exact delineation of where statistics ends and where machine learning starts, or where nonlinear dynamics begins, etc. I'm not interested. What I'm interested, from my perspective at least, is here are a suite of tools and methods that are available to us to solve a matter of urgent societal priority. We will use any and all of those tools. And when we need to, when those tools are not appropriate enough for the kind of solutions that we want to build, we will adapt those. If necessary, we'll innovate on those. If necessary, we'll collaborate with others. And we often need to collaborate. That's my personal lens. Okay, with that, let me take you through some basic ideas and case studies. Natural systems, natural earth systems. This is from the IPCC, the United Nations Intergovernmental Panel on Climate Change. And what it shows in the projection mode is the following. If you look at this graph, on the green part of this graph, that spread, that variability comes from greenhouse gas projections. We do not predict greenhouse gases, trajectories of greenhouse gases going 10, 20, 30, 50, 100 years. We do what if scenarios. What if the Earth, what if human planners were to do this? Then we would get this kind of scenario. So it's more what if, and that's why we call it projection. That's that big range in green. And conditioned on any of those projections, we say here is the plausible future that we expect. Then we have the blue. The blue is what we call multi-model spread. Different models, there are 40 or 50 modeling groups across the world. And how do models build by them? What kind of spread do we have? And here we are talking about global temperature. What kind of spread do we have? So in a sense, this reflects our knowledge gap. It's like saying F equals ma is Newtonian dynamics, and we know that. Nothing works according to Newtonian dynamics on this planet Earth. If you push a body, it doesn't stay in uniform velocity kind of motion. It stops because of friction. We do not understand friction. Therefore, we say F equals K ma. K is a parameter. It encapsulates all that we do not know, in a sense. And then different modeling groups, as a rough analogy, they have the same signs, F equals ma, but the way they do the K, that parameterization varies. So that blue reflects our knowledge gap in that sense. The orange is very interesting. The orange is internal variability of the system. Even if we knew the greenhouse gases emitted exactly, and even if we knew the exact physics of the entire Earth system, which is pretty much impossible, but even if we knew, we would still have variability, and that is the internal variability of the system. Some of whom you have heard about chaos, chaos as in the mathematical theory of chaos. Maybe you have heard in Jurassic Park, or maybe you have heard in mathematical equations. It's sort of similar to that. There is internal variability, even if everything is the same, and it's hard to assign likelihoods to those, so we have to design around those. If you look at this orange and the contribution of this orange, over the next 10, 20, 30 years of projections, that is often your design window, decision window. Over that period, the trend is comparable to the variability. And the overall variability is often dominated by this orange, which is this internal variability, intrinsic system variability. So it's important to address. All right, so this comes from Intergovernmental Panel on Climate Change. Here is something from our own work. This was published in Climate Dynamics by somebody called Devashish Kumar. Devashish is now working in Atlanta in a natural hazards risk management company. He's actually from, he did his undergraduate from IIT Kharagpur. So look what he found here. So this is at the top, these two are temperature, bottom, these two are precipitation. And look at the contribution of the orange. Global scale, it's low compared to the multimodal spread, knowledge gap. Precipitation, even global scale, is high. But as you go from global scale to higher and higher resolution to the scale of cities, on the whole, this contribution of natural variability increases. Right? So this is in the Earth system model, this is how complex the systems are. Coming from Earth system sciences to Earth systems engineering, if you will, if you call it that, systems that are interdependent. I was talking about floods in Kolkata. I understand from Udit that there have been floods in Ahmedabad. And of course, there were floods in Pakistan recently, which could happen in India also. So if you think about those kinds of things, not just floods, landslides, many other kinds of hazards, the infrastructures, whether it's protective infrastructure such as dams, levees, or whether it's lifeline infrastructures such as transportation, water systems, communication systems, power, energy systems, these are interdependent. And one of the things that's happening in recent years and has been intensifying is we are seeing not just extremes intensifying because of various things, climate change, greenhouse gas induced climate change, but also urbanization, things like that. So we are seeing that, but we are also seeing greater interconnectivity, which means that if a failure happens somewhere, the probability of that failure cascading. So there is one failure in a power grid, the probability of that percolating across power grid and causing a blackout like happened in 2012, right, Udit, in India. And then that cascading to railway systems and other systems because of signals and so on. Those probabilities are increasing significantly, right? So cascading failure, and it's hard to predict those. It's hard to quantify, characterize those. So in engineered systems, designed systems, built systems, that's a kind of uncertainty. And the same thing, by the way, in certain kinds of natural systems, such as ecological systems, ecological networks, food web. Okay. So that's another kind of uncertainty. And our own work, this is a paper in IEEE Transactions on Intelligent Transportation Systems by a former PhD student, Kevin Clark, and others. And Udit was involved in this one too. So if you take a look, that's one of the things we're looking at, some fire somewhere in one airport, some snowstorm somewhere, and how these things percolate across the US national airspace systems. This is just one example of that. The other thing, which is incredibly important, and I just want to mention it here because it's so important, although I must confess I do not have any expertise there, if I have any expertise anywhere these days, but this is important, and if we don't know, then at least we should collaborate. This is in the social sciences and economics. We cannot solve problems which are these kind of societal priorities without at least understanding the challenges. So this thing that I have here, this framework is from Professor Elinor Ostrom, who won the Nobel Prize in Economics in 2009. And she proposed this idea of how to deal with, if you think of tragedy of the commons that we have. So we think about environment, whether it's water, whether it's air, we think about infrastructures, transportation. None of us, well, all of us own it. Therefore, none of us own it. If you think of the World Cup soccer, football, right? Some of you, I'm I hope you're watching it, and I hope you're also supporting Messi. Just kidding. But if you think of there are news reports I hear that when Japan plays, and whether they win or lose, by the time the spectators and Japanese fans leave the stadium, they're perfectly cleaned. That's an example of maybe not tragedy of the commons. That's an example of common ownership. Versus in some other parts of the world, which I will not name, that's not how we take things, right? So tragedy of the commons, how do we handle it? And Elinor Ostrom talked about polycentric management. I'd encourage all of you to read at least her Nobel Prize lecture and view that. It's amazing. And some of the things that we said, at least in a policy framework, is that there is this vicious cycle of policy myopia, right? Short-term vision. Disincentives, financial instruments, disincentives, engineering stagnation, outdated best practices, which prevent action. But the thesis, at least for us, is that it doesn't take a whole lot. It takes some transformational science and engineering, and it takes maybe some financial incentives and some entrepreneurial spirit to turn that cycle from vicious to virtuous. And I'm hoping many of you, the bright minds here, the bright young minds here, where many of our generation, we have failed, you will succeed in that. All right, so bringing it all together, then here is the challenge. In the natural systems, it's chaos and natural variability. In engineered systems, design systems, or even in ecological systems, it's cascading failures. And in complex systems, it's tragedy of the commons and the need to handle this polycentric management. And we have to somehow handle each of these things well enough, whether individually or collectively or through collaborations. We just have to do this to be able to address this major societal problem. Climate change has been called the defining problem of our age, not by me, but by United Nations Secretary Generals. So if we have to address this, we need to do certain things. Just talk will not be enough. Talk is needed, maybe. Just that will not be enough. All right. So now let me come to a little bit more specifics on climate uncertainties and where we are. I'll cover this a little bit quickly. But again, please feel free to read our papers and such. So here are these two reports from Bloomberg, February 3, 2020, and then March 4, 2022. The climate models that they're talking about here are essentially the same generation, CMIP6. In 2020, they say climate models are running red hot and scientists do not know why. That's a strong statement. And then in 2022, they said scientists have an answer. With my limited understanding of climate science, the science doesn't progress like that in 2 years. From do not know to have an answer is not how, to these big problems. Something is getting missed in the way we handle these things, in the communication of these things, and so on. I'd encourage you to read why they are saying that. I'll not go through that in much detail. But one of the things is this knowledge gap that I was talking about. If you think about these large climate models, these require some of the world's largest supercomputers, such as the biggest supercomputers at the Oak Ridge National Laboratory, for example, where I used to work for 7 years. So they are run, they are archived, but how do you evaluate them and use them in the projections? So at the very least, you have to do two things, which all of you here will understand from your AI and data science background. We have to compare with observations, and that's called skill, model skill. But that's not enough, because in climate, things are changing all the time. So unless you're talking about something fundamental like Newton's laws of motion, which in the climate time frame will not change. We are not going into the Einsteinian frame of relativity. So we're still in that Newtonian frame. But beyond that, anytime you're going into something where it's parameterized and things like that, where the physics is not understood perfectly from first principles, which is in most of the things that we care about. If things change, those parameterizations will change. So now what happens? You have to compare and look at how these models performed in the past, but you also compare these models with each other. And then the third thing, which is what we tried to add in a Bayesian framework, is we said, okay, what about if we have variables that are related to each other, correlated to each other, or there is some sort of physical dependence, mechanistic dependence, can we use that third factor and develop a big Bayesian scheme to address all of that and evaluate these models in specific contexts, such as in precipitation extremes? This study was led by Evan Kodra, and again, Udit was involved in that, right? So that's, and I would encourage you to read this. If I start discussing those Bayesian schemes here, it'll not be an interesting talk. But if you read those, I'm sure you find this interesting. But if you do read those, please also read the online supplement, which has most of the information. All right. So there is skills, consensus, and physical guidance as we think about these uncertainties. Now let me take you through a few examples, just one or two examples of what you can get with these many different model ensembles, simulations. And as of now, I'm thinking about multiple models and greenhouse gas emissions. So if you remember that curve, I'm thinking about the green and blue part, not the orange yet, not the internal variability yet. So you can get things like what are happening to heat waves. Heat waves are intensifying, but potentially the uncertainty and geographic variability is higher than what we thought. This was an old paper, 2009, Proceedings of National Academies. Cold snaps. Overall, we are seeing warming, global warming, but that doesn't necessarily mean that the entire curve is shifting. What is happening to the mean doesn't reflect what necessarily happens to the tails of the distributions. I know that in machine learning and AI, recently there have been a lot of discussions around tails of distribution. It's hard to address any model. Whether it's data-driven model, physics-based model, tails are always hard. But here what you're seeing is that those cold snaps, despite global warming, the cold snaps, which will grow less in frequency, the ones that do happen may still be as intense and as long-lasting, and sometimes more intense and more long-lasting than what you've seen before. So this is a sort of counterintuitive insight, and hence it was highlighted in Nature. This paper looked at differential. So now we go, this other thing that I showed, those two papers were sort of more in the climate science, climate extremes, insights on that. Now going towards impacts, and I'm just picking one or two examples. This is indices, climate indices relevant for impacts. This particular index is about coastal upwelling, which is one of the most important criteria, one of the most important index when it comes to marine ecology. Some of you may not care, I care for fish. Some of you may care about other things. Marine ecology is incredibly important in general for urban coastal systems in general. Coastal upwelling is a process that sustains that through overturning of the marine ocean, and it's driven by wind vectors, which in turn are impacted by differential land-sea heating because of global warming. So this was a big open question in this area, that what is happening to coastal upwelling because of global warming? And what we found is that, yes, it is intensifying, and we found this from climate model analysis, multiple models, and spatially it's growing more homogeneous over time. Right? So this was published in Nature. Again, all of these are examples of things you can get from these large Earth system models. And then, insights on climate science, insights on impacts relevant for climate science, climate ecology, etc. Now let's come to the orange part, the internal variability. So if you look at these figures, the ones that are unshaded in the top 6, I have 3 different models. These are all US models, and the map, of course, is of US, and 2 different initial conditions. These are very small changes in initial conditions, 10 to the power minus 14, not detectable by any sensor when the model is initialized. But look at the differences in the projection variability. This is P minus E, precipitation minus evaporation. I take a 10-year average and then I subtract over 30 years. In a mass balance sense, this gives the total amount of water that's there in that part of the world, of the US in this case. And look at the difference. Now, if you do an average, and what I have under the shades are the averages. So what I have right below here, bottom right, is the average of the averages. What the average of the average shows is that there is no change, not that much change. But I cannot design based on that. I cannot operate my systems based on that, because that is like operating. I was just discussing with some of Udit's labs, students in Udit's labs earlier. That's like saying that I can build a bridge based on average traffic. That bridge is destined to fail every so often. So I have to consider this range of variability. The other way to think of it is that some years I'll get floods, some year I'll get droughts. 50 people will die because of floods, 50 people will die because of droughts. The total number of people that will die is 50 minus 50 equals 0. If you're happy to live with that, thank you very much. But that's not how we design, right? So that's the overall idea here. Now, how do we handle this kind of variability? This internal variability is hard to assign uncertainties there, hard to come up with Bayesian frameworks there. So here we have to come up with risk frameworks. Here we looked at, for example, in the context of energy production at risk, right? Looking at various things, warmer waters, scarcer waters. And what we are saying here is that despite the huge amount of variability, overall, there is a tendency of at least some of these to get into the scarcer and warmer regions, which leads to energy insecurity, and therefore we have to do something about it. This was joint work with US Department of Energy. The person who worked on this mainly was Poulomi Ganguly. She is a faculty now at IIT Kharagpur. All right, now bridging these gaps across scales. So we are talking about infrastructures, whether it's transportation, whether it's buildings, bridges. For example, we could talk about agriculture, we could talk about coastal systems, and I just give you a few examples. You have done work in many of these areas, but how to bridge the gap between these large Earth system models, which were designed to understand things like atmospheric dynamics, ocean dynamics, and what happens at the scale of infrastructures or agricultural systems or coastal systems. There was a perspective article in the journal Nature, which talked about how machine learning is starting to address these gaps. They talked about 4 areas within machine learning and how they have been used within Earth system models or are being used. These were initial examples. One of the 4 examples that they chose is based on super resolution and fusion. And this was our work. This is work by one of my former PhD students, Thomas Vendel, on statistical downscaling and fusion, how to bring those, how to use, for example, convolutional neural networks and things like that to, and broadly computer vision to map these, functionally map these. So, yeah. So what he did, and this was his award-winning paper, by the way, Ivan Kodra, about whom I mentioned earlier, was also involved. This is Thomas Vendel, and this was joined with NASA. So what this did was this was one of the first work that came up with a practical way to use computer vision to address this climate downscaling problem, if it's as it's called, right? From Earth system models to the scales at which stakeholders make decisions. And then what was done, and I'd encourage you to, by the way, read these papers and you'll find enough equations there. Udit, this is for you since you only want equations. I'm kidding. So this is, I'm picking on Udit today. But this is, the next part of that work dealt with how to assign uncertainty there. So if you go from deep learning to Bayesian deep learning, the thing here, Bayesian deep learning is not our invention. It was Kendall and Gal, Yarin Gal and so on, and others. But the idea was at that point, and as you know, AI machine learning progresses very fast, but this was 2018. At that point, most of the assumptions of Bayesian deep learning was with Gaussian data and Gaussian processes, and that won't work for us. So what we tried to look at is what happens if you start to look at skewed data and skewed processes. All right. From there, let me take you through some examples of bridging different scales, not all of which, maybe not any of which, uses yet these kind of statistical downscaling. I have a lot of heartburns over using statistical downscaling just as is. And there's a reason for that, which we can talk about eventually. You have to be careful about using statistical downscaling, especially since the climate changes, and question is, do those functional mapping, can it keep up with the change? Anyway, so here, this is work by my recently graduated PhD student, Kate Duffy, and collaborator in ecology. So Kate's work looked at very different scales. One is, again, these Earth system models, climate, and another is ecology, but very specifically ectotherms, cold-blooded animals. So we are warm-blooded. What that means is we have at least some capacity to adjust to fluctuations in temperature. Cold-blooded animals, such as insects, do not have that capacity. So they are very much susceptible to changes in temperatures. So what Kate was looking at is, what does that mean? This is an interesting way to capture some of our insights. The average of the behavior is not the behavior of the average. I know it sounds profound or it sounds nothing, but think about it, it may make some sense. Now, in the context of ecology and in the context of insects, for example, which are important, very important overall for the world's ecology and for all of us, really, what she found is that although there are diverse impacts across ecological systems and 38 species of insects, by the way, this information about thermal performance of insects were derived from field studies and laboratory scale studies versus these large scale Earth system models. You have to bridge these two. And what she found is that despite very diverse influences on insect population because of changes in temperature, in addition to changes in the mean temperature, it is changes in the fluctuations of temperature that cause additional risk of survivability of the species of insects. So this was published in Nature Climate Change just this last month, November. And again, I'm not talking about everything that we have ever done, just a few examples. So here, for example, we now looked, that was ecology. Here we looked at, we have been looking at transportation systems, both at urban scales, Boston, Washington, DC, and at regional scales, such as US Airlines Network and Indian Railways Network, cities like London. A lot of this work was initiated, at least in my lab, by Udit, and a lot of others have worked on that, including Kevin Clark, whose work I showed, Dishant Yadav, who actually is also from one of the IITs, IIT Guwahati, is now working at Microsoft, etc. Microsoft AI, Azure AI, etc. And broadly, the focus of this, and again, I'd encourage you to read all of these papers, visit my lab, sdslab.io, and you can see those. So what we are doing here is trying to use machine learning, computer vision, machine learning, to develop explainable insights about Earth system science. This work that on the very left, this uses, I would say, computer vision, again, convolutional neural networks, but with saliency maps, to try and get insights from different components of climate systems, such as atmosphere and ocean, and what do they mean for places where we humans live, river systems, urban systems. That bridging that gap in an explainable way is the intent of this work. This is there on arXiv. It has just recently been accepted in Nature Communications. I can, it's still an embargo, so we cannot talk about it too much. But, so that can go to the heart of one problem within Earth system model, which is this issue of how to deal with coupled systems, atmosphere, ocean, land. The other is this Bayesian deep learning, which I talked about. And then the third thing is graphical models, technosocial systems, which is, for example, urban networks. So now coming to these deep learning kind of models, these are incredibly useful for us. I already showed you some examples. I mean, when I say AI in this context, artificial intelligence, I'm looking at a broad definition. Whether it's in the Earth systems, it can be computer vision, machine learning, spatiotemporal machine learning. In the engineered systems, ecological systems, it can be graphical methods, technosocial methods. In social systems, it can be agent-based methods, participatory modeling. So a broad definition of AI. But as we all know, machine learning remains incredibly important. What is the state of machine learning, though? We are in this bold era of foundation models. We train our models with something, lot of data sets, and somehow it's able to find things about something else. I haven't used foundation models as much, by the way, but these are trends that we all follow. I'm sure all of you follow this. And we are in a situation where some people, this was an article in Proceedings of National Academies, both of these are, some people are talking about unreasonable effectiveness of deep learning. We do not know how to explain it, but hey, it works. There's always a problem with that approach. And there have been AI winters before with this approach. However, we cannot ignore that. If it works, we cannot ignore that either. Versus this other thing where they're trying to say, can we reconcile machine learning practices with things like Occam's razor, bias variance, trade-off, etc. So this is something we are still struggling with in machine learning versus when we try to bring it to statistical downscaling in climate, the issue is we have to go beyond what is called generalization in machine learning, that it works for out of sample. That is there here, but also remember the nature of the system is slowly changing. The Earth will not become like Mars or Venus in 30 years or even 100 years, hopefully. But the one place might begin to look like another place in terms of climate. The climate things might change. And can these systems address that? If there are issues with out of sample, then there are even more serious issues here. With that, let me come to certain things. Okay, with all these things, we have some understanding, predictive understanding, climate system, impact system, adaptation, mitigation. We know there are uncertainties. It's important to characterize the uncertainty and then deal with it. But how do we then go into action? So I'll cover it a little bit briefly here. I wanted to lay the background just quickly. In atmospheric science, Nobel Prize was awarded in 1995 because of the ozone hole problem. There was a paper in Nature in 1974, which was the basic science, atmospheric chemistry in that case. It led to globally coordinated action. The Montreal Protocol was finalized in 1987. 1995, Nobel Prize was awarded. And scientists are saying that this is successful. There are successful amendments and everybody's signing off on that. Wonderful. Science leading to globally coordinated action. And on the sideline, there was also a Nobel Prize. Great. What is happening with climate? It's almost as if the chronology is reversed. The Peace Prize came first, 2007. The Economics Prize, which talks about adaptation mitigation, came in 2018. Nordhaus and Romer talked about technology and adaptation and impacts of climate and the economics of that. And the Physics Prize, which talked about the basic natural sciences, that was 2021. Dealt with simulations of climate, attributions in the context of climate, complex systems in general. What is going on here? And the other thing is, look what one of those Nobel laureates are saying. I hope that young people succeed where we scientists have not. And climate pledges are falling short. These two are not comparable problems. The challenges are not the same, but it's important to think and understand what is going on here and why. Anyway, the other thing is, each nation, this lesson learned is based on a simulated, what is called war game, a simulated role-playing exercise that was organized by a think tank in the US, where I was actually a part. lessons learned from these things are that nations and states and regions will always think of their own interest in terms of resources, hazards, population, movement, migration, even as they think about mitigation and emissions and climate action and climate funding, right? So with that, some of the things I hear from my students, for example, is, Professor, you just talk and publish and take brownie points with your former students like Udit, but we don't do anything serious. Okay, so some of the action needs to happen at local scales and regional scales. And never let anybody tell you that there is this big disparity between global scale science versus local scale problems. Most major science anywhere in the world often comes from local scale challenges, regional challenges, and how they move bottom up. Not all of them. There is string theory. But by the time you come to these kind of problems, right? So often action has to be taken at those scales, and then cities come together to take action. So here is, we have been working with the city of Boston, where our university is located, Climate Ready Boston. I was leading in 2016, leading this extreme temperature. Evan was a part of that team, etc. And we have done some work in a small town within Greater Boston, which is called Brookline, looking at public health impacts of urban heat waves, looking at not just the heat waves, but also vulnerability and exposure, demographics, population change, etc. And one interesting thing is once you start doing these, then people pick up on those. So here is an example of some assessment that was done just last year on climate change impacts for Greater Boston area, where I was not involved, but two of my PhD students, Kate and Lizzie, were involved. And former PhD student Evan, who was one of the team members there, he was leading the temperature extreme section, right? So these can gradually spawn off. And in terms of translation to startups, so one thing that I say is, in the US, increasingly in India and across the world, humans have significant entrepreneurial spirit. Some of that in India, we even call the good side of Jugaad. There are many sides of Jugaad. I'm talking about the good sides of Jugaad. Like that Mars mission that India had, which cost less than the movie Gravity, which is true, right? Anyway, so why not bring that entrepreneurial spirit if we are really saying we want to solve this major problem, societal challenge? To give an example, when this person, Dr. Karen Clark, this was late 1980s and early 1990s, she was saying, she was going to the insurance companies and saying, you guys need to do something about natural catastrophes. You guys will be dead in the water, literally and figuratively, if something major happens. The insurance companies gave her polite hearing and said, thank you very much. And then they said, nah, it's just act of God. And, God is really not in this picture. It's all inaction of humans, but okay, it's act of God, nothing we can do, it's rare. And then Hurricane Andrew happened in 1992. And some of the insurance companies went bankrupt, and many of the insurance companies and reinsurance companies are those companies that insure the insurers. They went out after Karen Clark. Where is this lady? We need to talk to her. And that's how this whole business started 25 to 30 years back. And of course, when something starts, the initial spark starts in Boston and then it spreads to California. So I'm just kidding. This is a US-centric joke. But then Hemant Shah and others from with some Stanford or some such university there, they started this catastrophe. They focused also on earthquakes. So Karen Clark focused on hurricanes, they focused on earthquakes. So these two remain the market leaders. Similarly, now with climate, what needs to be done is bringing these things inside it. And I'm very proud. This is the picture of my former PhD student, Dr. Evan Kodra, who co-founded this company called RISK, R-I-S-Q, RISK, which looks at urban risks. So it looks at urban equity and it looks at climate models observations to handle urban risks, and then it monetizes that. To be a private sector startup, you have to monetizes that through municipality bonds in this particular case. This can generalize beyond to other cities, but also to entire nations. And there was an article in the Wall Street Journal about that. And again, what is needed for this to pick up? I mean, this was acquired by a Fortune 500 company. So there is some awareness, more awareness about climate change, I would say, than what Karen Clark faced 25 to 30 years back, but still more needs to happen. And hopefully we won't need the equivalent of an Hurricane Andrew, because in the context of climate, it'll be much worse. We won't need that kind of thing to revolutionize this industry. And again, just as I was giving this earlier example, once you start something, others pick up. This is my former PhD students, Kate Duffy, about whom I spoke earlier, and TJ Vandal, who were scientists at NASA. And through NASA, they started their own company, which is called Zsai, which is about real-time weather prediction using AI. Couple of things before I end. One is, in climate and environment, justice and equity are incredibly important at different scales. In our work in Brookline, a small, fairly prosperous town within Greater Boston, we found pockets of inequality, deep inequality, in the context of public health impacts of heat waves. In the context of whole nations, this is where we are. We are talking about annual per capita electricity use. We are talking about Human Development Index. Here is where I'm from right now. I'm not happy about this. But here is where India is. Question for India is, does India want to go from here to there? Or does India want to go from here to the Scandinavian countries? Same Human Development Index, but very different per capita electricity use. So again, I'll end with a couple of quotes. In some recent quotes, there was a Newsweek article which talked about global weirding. One thing that I said to them is, in addition to everything else, we need to be very careful about predictive surprises. It's probably more important to understand how surprised we might be in the future and how to deal with that, how to make ourselves resilient to that. And then there was another article in New York Times where they're talking about rebuilding after hurricanes. And I was talking about, the importance of performance-based design, not just prescriptive codes in design, the importance of gray-green infrastructure, nature-inspired systems, and the possibility of relocation from some of the most extreme places of extreme risk, but that relocation has to be done in an equitable way. With that, thank you very much. So while they're coming up, if we don't have time for questions, I know I exceeded my time a little bit. Please go through the papers. Please go through the lab, sdslab.io. And I have my, it's just, you can send me emails at my first name, auroop@gmail.com. I'll try to address them, but you'll have other contact information as well.
If you have any question, we can take at most one question. So perhaps, yeah.
Yeah, hi. So I want to ask one question, that the progress of AI and machine learning in climate science. So if we are able to develop some algorithm at some place, like having some climate change or something, or basically I'm able to project what is going to happen next 30 years or something at some place. So basically, will I be able to replicate that kind of algorithm to some other place sharing the same climate or something? Have we advanced that much in machine learning or AI?
Yeah. So these are called method of analogs, and there indeed are existing papers and such. We deal with those. I'm not saying that that line of research has been exhaustive. There's a lot more to do. But there have been, has been a whole line of work dealing with method of analogs, such as how cities will look. So if you're familiar with the geography of US, for example, right, there have been in the National Climate Adaptation of the US, New England, which is north and east, coast, there is feeling that the climate there might start to resemble the climate of North Carolina going south, right? Just as an example. But yes, definitely, I mean, think of the standard k-means algorithm in time series. So where you look for neighborhoods, not neighborhoods based on geography only or time, but neighborhoods as in similarity. Extend that k-means algorithm to time and space now, right? In space, it's called method of analogs, but time and space. And then you see, okay, how does this work in climate? And maybe not just so, your question was about the climate science part of it, atmospheric dynamics, ocean science, land surface. But why not also think about this from what the impacts will be on various systems? And yes, I think that's a very promising direction. So like I was saying, the climate of Delhi may not start to look like climate in Venus or Mars very soon. Although these days, I mean, in the summer, if you go to Delhi, it almost feels that way. But it might start to look like the climate in some part of Rajasthan in terms of heat waves. Can lessons be learned from there? Absolutely. And there are research lines doing that, very interesting research lines, a lot more to be done. Thank you for that question.
Thank you, Auroop. And here is a small token of appreciation.
Thank you so much.
So the next speaker for today is Professor Chiranjib Bhattacharya. Professor Chiranjib Bhattacharya is Professor and Chair of Department of Computer Science and Automation at ISC Bangalore. His research interests are in foundations of ML, optimization, and their applications to industrial problems. Professor Bhattacharya is the Fellow of Indian Academy of Engineering. His talk is titled Latent K Polytop, Convex Geometry Meets Generative Modeling. 10 minutes, I'll give you a soft signal, Professor Bhattacharya. Sure. That's it.
Hello? Yeah. So good afternoon, all of you. So the question to the organizers is, before I begin, when is the coffee break? I hate to be between coffee. Okay. First of all, thanks to the organizers for inviting me. It's a pleasure to be here. So this talk will have equations. I'll make up for it. So yeah, so here I thought I will talk about some of the work we have been doing. It's called latent K polytope. That's new to most of you. Don't worry, we'll parse that. So the idea is we'll talk about not so fancy things in machine learning, which is often called as unsupervised learning. So one of the ways of looking at unsupervised learning is we have generating data, like models. So we have an idea of the world, where the world gives me data. I have to figure that out. So we will see a very nice connection between convex geometry, which is often studied by theoretical computer science, and machine learning. And let's see how much of these ideas I can get across to you. Yeah. So let's get started. So I was not sure the audience, so I thought we'll do a very generic introduction to AI and to help set up the talk. So maybe 100 years ago, or even more, 120 years ago, this was one of the questions which, the scientists of the day were pondering about. Can machines think? Now think about this question. See, thinking, when you say thinking, probably is human beings you're talking about. So neurobiology involved, philosophy involved. What do you mean by that? And then this was coming up, industrial revolution was coming up, this matured to a degree. We had at this point railway lines, we had some machines, people are going, I can see the guns were involved, so there is some development of material civilization. So this question, it borders on engineering to neurobiology to philosophy, and often, of course, it goes also into religion and other kinds of things, spirituality. So this was a vexing question until today it remains so. But then a very interesting breakthrough came. No, I didn't know Hollywood. So this Alan Turing made this very interesting, the case. So think like this. In this very famous paper in a computer machine intelligence, and those of you who haven't read it, I strongly recommend you read this. For those of you who haven't read it. So there, the case was made as follows, modeled on a parlor game in England. In England, there's small fairs and there's a parlor game that the game was that in a room, suppose, there are two rooms and you can only exchange questions. You have to figure out whether, and you can look at the answers. You have to figure out whether there's a man or a woman. And you just get from the answers, you have to figure that out. So from that, he said, modeling on that, he said, look, what if there is an interrogator, let's call them C, and in the room, one room, there's a machine, and another room, there's a human being. I give the same set of questions to both. And if I can make out, or if you cannot make out that which room there's a machine and which room there's a human being, maybe I'll say the machine has passed the test, the machine is intelligent. And that being called a Turing test. So as you can see, and this to date, as I see AI, this to date seems to be the field is trying to do. That's why you will see fancy tools, right? What happened? See, what is AI today? AI is that tool which helps me recognize images. Recognize like what? Like humans. So mimicking humans. That's what Turing test is all about, right? So, human-like vision, right? This is, for example, collage of pictures taken from imaginary data set. I mean, probably this is one of the things which shows that machines can get human-level vision. We have these fancy tools like Alexa and Siri, which has conversation capabilities. So many of these things are happening. And today, definitely, we would like to think that we are living in an era of almost AI has revolutionized our lives, right? But let's look at it closely, and you can see here, from Alan Turing's days, where that paper came out in 1950, I guess. Then at that point, people thought about neural networks, tried to bring the human brain. The first machine, I think, was built somewhere in the 1950s, which is called perceptron then. But really the first, more or less commercial, I won't say commercial, but most interesting system where, I think there's a machine built to recognize human voices. I think it's called NetTalk. It came out in the 1990s. But after that, there is a steep jump. Now, this is what I mean is number of neurons, 1 billion neurons. And these are today's industrial models, which some of them, many of you use, for example, ImageNet and things like that. And now it's predicted that by 2025, we'll have models which will have 100 trillions. I do not know what that will do. We already see fantastic things like Flamingo and others, where large neural networks have been built and doing very interesting things. For example, GPT-3. Now, the sobering thought, like we wanted to, Alan Turing's dream, right? If you can fool a human into thinking that you're like a human, probably that machine is intelligent. Now, if you want to, but let us, a sobering thought is, if neurons are like, if the neurons in neural networks is like a human neurons, so our human brain has roughly 100 billion connections, and we're talking 100 trillion here. So maybe we are not doing things, maybe there are more things at play here. We have to engineering wise, to do better, right? So this is causing, so maybe we have to look for alternatives. So now I don't know why it's not. So one more sobering thought is that more number of neurons I add, I have to also train them. Parameters I add, I have to train them. And now a rule of thumb seems to be that if for the linear regression, rule of thumb seems to be if you have 100 parameters, you will need at least 1,000 data points. So this is sometimes called, this is of course for linear models. But this other important problem is that, for ImageNet, for example, you want to develop a system which will identify all kinds of objects and classes. So you need that kind of label data. Now imagine 100 billion, as we saw, the number of neurons, number of connections is like 100 billion and things like that. So, and our theories, whatever theories we know of today, says that you need 10 times parameters, and this will even go worse for if the systems are nonlinear. Then high quality, large number of labeled data, so many parameters. This is creating new kinds of job opportunities, I would say. Like, for example, there is a thing I copied from an advertisement. See, the startup company is asking somebody to, can you label data for us? So there are new age jobs coming up. So now, as you can see, this is also expensive. So where are we going with this, And coupled with the fact that every time we train our neural network models, right? So, how much energy are we spending? So here is some data, which says something like this. So these models, I know some of you have played. Sorry, some of you have played. This is BERT. I know these models, I think some of you have played with this, GPT-2 and things like that, right? Now, this seems to be, there's a measurement. This paper has measured some of these things. And it says that this is the amount of energy you consume, for one iteration of the training process. Okay, this number doesn't make much, doesn't appear much on its own. This carbon footprint, if one can measure, is something like this. It still does not make much sense unless I compare with something else. So probably this is a more important thing. See, for example, if you travel once in a plane from New York to San Francisco, your carbon footprint is like 1984, 1438. This is one iteration. If you do a transformer model, this is the carbon footprint you have. An average car in US, this is the carbon footprint. 6 times more. So now, of course, after this paper came out, there are a lot of this discussion that maybe these numbers are not accurate and things like that. But even if they're a factor, if they're off by a factor of 2, it's still alarming. So is this the revolution which we are looking for? So let's hear some of the leading figures of the day, what they say. So for example, Liezi Yanlipun, and he clearly disagrees. This is not the way to go. And says that if AI revolution will come, it will not be supervised, as he says. Allusion to that we probably need other kinds of paradigms where we don't need supervised models. So, of course, so say that what are the other paradigms one may want to think about? But let's think about what's wrong with supervised models. Apart from its high cost, its high energy, because you need more parameters and things like that. So one of the things is that it is not, so things, ImageNet can only see. It cannot talk to you. Human beings can see and talk. So this is something called narrow AI tasks, right? So we need other paradigms. And probably that will help us get to, machines which can exhibit intelligence like animals and things like that, right? And more importantly, even for business-wise, large amounts of data, large amount of training setups, things like that is very expensive. So it neither makes sense scientifically nor even to make in the business wise. So probably we should look for other paradigms. So need of the hour, as it says, is modeling paradigms which doesn't require supervised data, right? So one of the classical setups is unsupervised learning, which which I'm going to talk about. But more importantly, there are other paradigms now is coming up, sometimes called self-supervised learning and other things. It's a fascinating area. I think those of you looking for topics, PhD topics, I would definitely recommend proposing some of them. But for this talk, we'll look for more classical things like unsupervised learning. But the main thing is, the main challenge is there that, come up with rigorous formalisms like supervised learning, and which can have guarantees and also works well in practice. So with that sort of introduction, so one of the main challenges in supervised learning, as it seems, is that what can be the goal? In supervised learning, the goal is very clear. I have to build a machine or to predict. I take an image, I have to see is a cat or a dog. And the given is that I give you a few images labeled cats and dogs. From that, I learn, oh, this image is like cat. And I have to somehow, so that sets up a goal that every time, so any model I build, if you show me a new image, it's of a dog and I label it as a cat, I make a mistake. Fine. In unsupervised learning, how do I do that? What are the goals? So for example, one of the goals is people say like finding structure in data. Now to illustrate that, let's take this example. Suppose you went to the market, got a few fruits. Let's say there are apples which are colored red and oranges are colored yellow, and you have measured I do not know any two features, maybe their color and maybe their height. So you plot them, and there are 6 of them on both sides, right? So you said that okay, if I take 6 apples and 6 oranges, I plot them like this. So maybe, okay, so now our next data point comes. I don't know, it's apple and orange. What I can do is, based on this, I can draw a line like this, right? So on the left side of the line, if it falls, it's an apple. On the right side, it's orange. And I go from there. That's basically what the field is all about, right? Now think for a moment. I give you the same data points, and I don't tell you the apples and oranges. Now what is the goal I should set up now? What do you mean finding structure in data? So this becomes a little bit more philosophically not very well defined, right? So one of the classical things is, very widely used application is k-means algorithm. Okay. Now you can now if I ask, how many clusters do you see here? So this becomes a very difficult question, right? So even a simple question like how many clusters still remain open. So we in the recent past we made some progress. We try to come an algorithmic answer, but I've been involved in this, but it's far from satisfactory. So this is joint work with Ravi Kannan and Amit from IT Delhi, but it's far from satisfactory. So these are things we keep thinking about, and maybe this is a talk for some other day. So the point being that even simple questions like this, we have no answer. So this probably will define, in my opinion, probably a lot of hard science in the next few years to come. So now, so at this point, let us see then, of course, we can't do much, but can you do anything at all? For example, what are the models in unsupervised learning? What are the setups you think we can start examining? So a broad class of models can be thought about, or rather, we said what are the goals, right? So one of the goals is that finding structure in data is not getting me anywhere. So another goal could be that suppose I posit a model, and I say data is coming from that model. And now from the data, can you guess the model? These are called model recovery questions. So now so from data, can you recover the model? And now the question is that, more targeted question is that, can you recover the model from finite number of data points, not infinite number of data points? So these are often called non-asymptotic. And so one of the other questions is sample complexity. Like how many samples are needed to recover the model? Why is this important? As we saw earlier, right? The number of data points needed, that's money. So we'd like to have models whose sample complexity is low, but yet have formal guarantees and also works well in practice, right? So these are important questions which I think the field is sidestepping now. But hopefully in the coming days, this will become more important. So now with these two lenses, so let's look at some models like generative models. So generative models are models where, we have, there's probability laws which governs the data generation process. So now there are many examples of this, but to help set a context, let me do this with with an example to motivate you. So here's a problem I don't think can be handled by supervised learning problem. So this problem is about, let us say you have this pile of books. So this is I would say, civilizational problem. The first library in human civilization, as noted, was in Alexandria, 2000 years ago. From now till then, even till few years ago, library was the one place where information was there. And a librarian's job is to now somehow, this pile of books is there. You ask the question, I need to learn more about philosophy, I want to learn about history, I want to learn. So let me go read this book. Right? So now how do you do this automatically? So this is the field of what is known as information retrieval. I mean, there's a definition here written from this very nice book by Manning, Raghavan, and Stutze, classic textbook. You can find more of this. So basically finding information from unstructured data. In this case, assume it's text. It's 10 minutes now? Okay, so maybe coffee break gone. I've been around halfway on the talk. Okay, so fine, let me then speed up the things. So the point is that in the previous diagram, you could not see much. But suppose the red colored books are all history books and green colored books are geography books. Like, suppose there was an index like that. It would have made matters like so much simple, right? Now, instead of books, now think there are websites, web pages. How will I index those web pages? That will help me retrieve information. Right? So this is the bread and butter of most web companies, right? So one of the things was, it's taking time. So can we create an index in unsupervised manner, right? So because already I think Udit was saying 10 minutes, so I have to hurry up. So can you create an index in unsupervised manner? Because nobody can tell you, read all the websites and give you a label data for all these things, right? And should work on large volumes of data. Sorry. So one of the things was this interesting called topic models. For example, if a website or in a text, any document has this 5 words, run, inning, hit, season, game, what would the document be? Sports. Agree, right? I didn't require noun, verb, etc. to think about it, right? Maybe the patient, drug, doctor, cancer, medical, right? This is something with healthcare, right? So now you see this co-occurrence of these first 5 words maybe is an index. So this was the spirit behind this argument. And then, there's a lot to be said here. But at some point in 2001, this nice model came up called latent density allocation. And since then, it has been used very widely with a lot of success. Like, for example, it can tell you if it's a document, this document is about, a comparison between Nexus tablets and, iPhones. And it can say that, and you can see that it will say that, see, this document, this is about this topic. The first topic is Nexus tablets, where this denoted by this kind of keywords, and topic is this kind of keywords, right? So it's a very powerful tool, but unfortunately, not much is known about this. It works very well in practice. So I'm sorry, this is the thing. So one of the ways to think about is that, generating data from such topic models, right? So it is something like, think like this. It is something like, I have K topics denoted by a matrix M, and what we do is you sample, sort of M words, small m number of words from this distribution given by P. So M is, each topic is like a probability distribution over words, and Ws are the weights from this, right? Now, in such a process, when you do that, that was basically the foundation of sort of this LDA kind of models, where from this process, this complicated set of equations were there. And now the idea is, W's are the words I know, alpha, betas are some hidden parameters. Now all the magic is there is to compute theta and z. Now computation of this comes through these complicated equations. And it is not very hard to see that exact inference like this is sort of NP hard. I mean, it's very easy to see this, like looking at those equations, and when 5 minutes to coffee, hopefully you'll all agree that it's NP hard. But the point being this, I'm sorry, why is it? Yeah, I'm sorry, there's something wrong. So essentially, all this complicated mathematics turns out to be something like this, that assume now, suppose there's a topic of 2 words, right? So M1, M2, M3 are a topic, these are topics, and a document is suppose like a convex combination of them, MW, what you talked about, right? And now it's, so now this document is governed by these 3 topics with equal weight. So, and now this document is a draw from this distribution. So often what it means is that, why is this happening? I'm sorry. Sorry, there's some problem. Okay. So now here I could go to this talk, but I think there's not enough time to this. So we want to talk about how to set this problem in a geometric setup, where we talk about latent K polytope, where the latent polytope is essentially the polytope given by this how do I say this topic vectors, and then we talk about sample complexity of this. But I think, give me a moment. Yeah. So now, how much time? I think I don't have too much time here. So what I'll do is, maybe what I'll do is I don't have time to talk about latent K polytope now, the time as it says, but maybe I will like to take one message here. See, the main bugbear of this this whole setup is that the equations which we saw was essentially sort of finding out maximum likelihood. Now, see, the maximum likelihood is something like A is the data matrix, the corpus, as we said, and M is the topics we want to learn, and L is that complicated looking function, right? Now, from A, find M, which maximizes this function, right? And now, depending on the mod distributions, etc., algorithms will change and things like that, right? So this notion of fitting data to a model may not be the best possible. That is what we learned, because for 3 things. Even for LDA, finding the maximum likelihood, maximization is a difficult problem. Forget maximization. Computing the L is also a difficult problem. I don't know the objective function is, right? And lastly, most of these results, moment you invoke maximum likelihood, also remember, things are asymptotic. That only works when n is infinity. So this is how to get around this kind of challenges, right? So now, as it says, probably time is up. So maybe I will. Yeah. So this is the one lesson we learned, that fitting maximum likelihood models is not a good idea. Fitting the best model like this, so likelihood is concerned, this may not be the best idea alone. Why? Because it's intractable to begin with. You're rather better off saying that, can you have a recovery question? That is, suppose whatever algorithm you have is fine, but now can you prove things like this? Suppose the data came from our model M. Now can you come up with an algorithm which will give you an M hat, such that M minus M hat is less than epsilon, right? So that should be the goal. Now the question is that for a given epsilon, what is the minimum number of N you require? So these are the questions I think are interesting and important. And in our case, we could solve a problem like this, as we said. So now just to give you the latent K polytope at least that much we should do, since it's there in the title. So suppose, as you said, take these 3 models, a topic with 3 vectors, M1, M2, and M3, and assume there are only 2 words in your corpus. So now, what happened? Why is it working? Yeah. So as we discussed, suppose there's a point inside the polytope, right? Which is like we talked about P in the previous slides. And now So the green color thing is actually the data you see. So from M1, M2, M3, you decide that, maybe I need a document which is like 50% politics, 30% sports, and 20% maybe health, so and that you can get a point that, sorry, why isn't it working? You get a yellow color thing, right? And now green color thing is actually data you see. Now the next question is that you see your data is green colored things, right? From green colored things, can you get the pink colored dots? These are the vertices of the triangle, right? So now we do not know this polytope, right? That is that blue colored thing we do not know. We only see the green colored things. From these green colored things, can you figure out and the vertices here? This one, and this one. That is key. Now, what is different? Now, very simple question. I give you a data point, right? So what do you do? Okay. Now you can take a convex hull of them, right? It does not tell me, still doesn't tell me the topics. Topics are still far off. So this problem is essentially a geometric problem in computational geometry. So this is what we are trying to solve here. So this is, and one of the criticisms of machine learning is heavily borrowed from other fields. It hasn't given back. So this is one of the problems we see. We contribute back to computational geometry, And so of course, how much time do I have? Time over, right? Sorry, time over. So I'm safe actually. I was in trouble going further, but the idea was, to now talk about how to get to those pink colored dots, but maybe some other day if you invite me again. Thank you.
So we may have time for one quick question as we set up the next talk, as it used to be on it. Yes. I can repeat the question.
Okay. So thank you for this wonderful topic. I know it was not it was more, but it was fascinating. Now, question is, you talked about these are asymptotic. And as we know, these systems have problems. I mean, in general, data-driven systems, AI, machine learning have problems with extremes, with tails, with surprising behavior. Humans and animals have problems there too, but to a much lesser extent. In these kind of things that you're talking about, if you have a lot of data about, let's say, mass and energy, and if you were to send all of that information, human information in a spaceship, would you send all of that data or would you send E equals mc squared? And is there any place for that condensed information of E equals mc squared in this whole data-driven things? Is that supposed to be injected into those data-driven systems? Do they come out of those data-driven systems? And if they are injected, is there any hope of then getting better with extremes or surprising behavior? And coming to your information retrieval, in addition to indexing of frequent behavior, things that we understand and things that are there, can we actually read the Indus Valley script?
So you don't want the audience to go for coffee, right?
Of course not. Your lecture was stimulating enough.
Thank you. No, but I think a lot to unpack and a lot of difficult questions. So I think, of course, information retrieval, a lot has been done. I was just taking this as a cartoon example to motivate what we do, because that's one problem. You cannot have supervision. That cannot be solved supervision. So there are lots of good problems can be solved, and really new products will come in the next few years, which you will see are beyond the pale of whatever, give me data, label data, run my deep networks. This will not be able to solve this. So that's one of the things we are trying to propose here. Now, the question you made, right? Suppose I know E equal to mc square. Maybe then I have already, they don't need data anymore. So there's a very nice paper. I think we'll have to search that. Maybe your physics colleagues can tell us. Suppose you do not know F equal to ma. You don't know this. I come to a different planet. I do not know the physics of the planet, right? But I can do experiments. So it says that if you get enough Bayesian pairs and data, I will be able to guess that. The papers like that already showing, at least for gravitational laws, people can find this, there are papers like that out there. At least they have shown empirically, right? So probably the merit of this kind of discussions is where you do not have such crystallized knowledge of the world like E equal to MC squared. I don't know that. I can only do experiments, and hence I require this. So now if you have such, so maybe that's the thing. If you have already know such things, then probably, of course, less data is important. And yeah, so but related to extremes, there is one more interesting thing, I think. So what, I mean, my understanding of unsupervised learning is that what is notion, the notion of distribution is very important. So this is Gaussian distribution. Now then I have some idea about the tails, which can tell me now that can be used to reason about extremes, right? But as I said, more discussion is needed, and I think audience would like to go for coffee, I guess. Otherwise, we would love to have this discussion.
All right. Thanks a lot.
Thank you. Oh, your question? So in this case, okay. So in this case, my algorithmically, yes, that I was to brag about it. So our complexity is the number of non-zero elements in data A into K. So it's linear in this. So K could be as large as possible. Having said that, now here comes the bad news. See, to say all that, I must have working code. I think the algorithm is still a little bit, this is more conceptual as opposed to say, okay, here's working code to give you. I mean, so I think still work needs to be done, right? Maybe some young minds would do that. Right?
Right. Thanks a lot.
Thank you. Thanks.
So before we go for coffee, we have another very interesting talk by our industry partners from Accenture, Mr. Kapil Gupta and Naveen Balani from Accenture India, and they would be talking about sustainability and AI and industry perspective. In this talk, they would be talking about exploring Accenture's thought leadership, energy efficient AI principles, engaging with green software community through GSFs, and introduction to environmental impact of AI and its criticality. So Kapil, I hope you can hear us. This is going to be a talk over the Zoom, and both of them are here. Kapil and I hope you can hear us, and we saw you, and we look forward to your talk. Thank you.
Sure. Thank you, Professor. Am I audible?
See, yes, you are audible.
Okay, thank you. Good afternoon, everyone, or good evening, everyone now. My name is Kapil. I'm part of Technology Sustainability Innovation Group at Accenture. Now, as a group, Technology Sustainability Innovation, or TSI, we are driving innovation at the intersection of technology and sustainability. I, as an individual, I'm a strategic area and asset manager for Green AI and data. So look forward to talking to you, look forward to interacting with you today. Maybe, I've been joined with my colleague, Naveen. Naveen, if you'd just like to take a minute and quickly introduce yourself, and then we get started with the session.
Yeah, thanks, Kapil. Good evening, everyone. I'm Naveen Balani. I'm a chief technologist with Technology Sustainability Innovation Group at Accenture, working on innovation and research in the intersection of technology and sustainability. And very excited to be here at IndoML and talk about this important topic. Over to you, Kapil.
Thank you, Naveen. So the way the agenda for our presentation today, our session today is what we will do is we will briefly talk about why should we explore sustainability in technology. Sustainability is growing in importance. There is no doubt about it. Global warming is there, so that's important. But what's the role of technology in there? So we'll start from there. We'll get into what's our framework, what's our thought leadership, how are we approaching this area at Accenture, sustainability in technology, and then we'll get specifically into the area of interest today, which is the green AI part of it. Naveen will be covering that, and then we end up with the foundation that we started around a year back, Green Software Foundation. As a founding member of that, we will briefly talk about that. So that's what is lined up from our end in today's session. So to get started, as I mentioned, the question comes, why should we talk about sustainability in technology? Sustainability in general is important, but why in technology? And while most of us appreciate the emissions that are happening out there, they should be reduced. Because when, let's say, when we drive on the road, we see a vehicle being driven by diesel or petrol emitting carbon dioxide, or there being carbon emission from there. Similarly, let's say when you pass through a thermal power plant, you see emissions happening there. But that's not the case when you pass, let's say, next to a data center, or let's say when you turn on your laptop, you don't see carbon emission coming out of it. So appreciation about sustainability in technology isn't there as much as it's there outside of it. But it's growing, and it has to be recognized, and the time is now. That's the thought process we have. Now, why the question is, why should we explore to it? Why should we explore sustainability in technology? And to answer that, the estimates are in 2020, ICT emissions were close to 4% of global greenhouse gas emissions. And the way digital growth is happening, the way the adoption of data and devices is happening, this could reach to 15% of global greenhouse gas emissions by 2040. So there's a significant percentage of global greenhouse gases being emitted by technology, and the number is bound to grow by leaps and bounds. That's what the estimates suggest. All of us love new technologies, but then these new technologies have their own environmental footprint. They have their own challenges. So let's look at cloud. The estimates are today cloud data centers that we have consume close to 2% of electricity worldwide, and that number is going to rise to 8% by 2030. Bitcoin, a very well-known example of blockchain, estimates again suggest the kind of energy it consumes is more than the entire country of Switzerland. AI, something which is dear to all of us in this session. The estimate, or kind of an experiment which MIT ran, suggested that training a simple AI model can consume or can kind of emit carbon as much as 5 cars in their lifetime. So the point is, there's a huge amount of emissions happening through technology, and it's going to grow by leaps and bounds. So that's the challenge that we are facing. Now, when there's a challenge, there's an opportunity. So the opportunity for all of us, for the industry, for the academia, for everyone is, how do we decouple the digital growth that's happening and that's going to multiply in future, so that we decouple it from the environmental impact. That's the opportunity that exists, and that's what we are trying to address here at Accenture. Now, the way we are approaching this area, sustainability and technology, is there are two parts to it. Sustainability by itself is a great technology by itself is a great enabler of sustainability use cases. So whether you look at it in supply chain or whether you look at multiple industries, there are new use cases coming up which are being driven by technology, which are enabling sustainability use cases for them. However, another aspect of sustainability is sustainability in technology, which is probably not receiving as much as attention as required. So that's what the focus for us in this group, Technology Sustainability Innovation, is. How do we embed sustainability in technology? And again, the kind of problem the world is facing, it's not about making small impacts. It's about whatever we do, it should be scalable. It should help us reach the goals that we have, that the temperature should not rise more than 1.5 degrees Celsius. So that's the idea is, while we are driving sustainability in technology or by technology, we have to do it at scale. So that's what we are addressing here at Technology Sustainability Innovation in Accenture. And how are we doing that? Especially sustainability in technology, that's what I'll focus on. When we talk about sustainability in technology, predominantly, we mean green software. The idea is you build your green software, you build your software in such a way that it emits the least amount of greenhouse gases while you are building it, while it's in production. So that's the idea behind green software. How do you cut down on your emission? That's what we are talking about when we talk about green software. Now, software by itself is a very broad area. And the point is, we can't solve all the problem in one shot. So where do we focus upon? And to kind of focus on things, we said let's narrow down it into certain areas, and we found out these are the 7 areas. Probably if we impact them, then the chances are high that we will be able to address a significant amount of emission which happens through software. And the 7 areas that we identified are first is software development lifecycle. Your choice of programming language or the practices that you use while you are building your software can have a deep impact on the kind of emission that the software will do over the life cycle. So that's one area we are exploring. We are working on it. We have multiple assets which are built on this. Similarly, let's say the UI design time, the choices you make, as simple as what should be a color combination of the UI screen, can have a significant impact on the energy emissions that happens from your software or from the UI. I mentioned about a simple case of AI model taking up or training an AI model emitting emission as high as 5 cars in their lifetime. A similar study, another experiment which was done was around accuracy, how much it costs to increase the accuracy. In AI world, all of us want more and more accuracy. But the point is, there is a trade-off. And the experiment that was done was around the flower detection. So there was the model was at the 96% accuracy, and the idea was to improve it further. And surprisingly, when we try to increase it from 96% to 98%, the energy consumption increased by 700%. So the key point is, when people are building the models, there is a trade-off, and what's the right one for you? That's what we are helping our clients. That's what we are helping our teams to choose under Green AI. And my colleague Naveen will talk more about it, the work we are doing under Green AI. Similarly, when you are looking at, let's say, distributed ledger technology, what kind of network design you have, what kind of algorithms you have, can have a significant impact on the overall emission in the DLT that you are built. In case of data, the estimates suggest 17 to 90% of all data is a dark data. This is something which we never use. It just lies there. So how do we ensure that there's a minimal replication, there's minimal redundancy in your data, so that the overall emission towards the storage of your data reduces? A lot of our clients, a lot of us are using cloud, but that just shifts the emission from my laptop or my data center to somewhere else. Now the point is, when you are moving to cloud, how do you choose a data center which has the least amount of environmental impact? So there's a team which is working in that area, guiding our clients. How do they choose the right cloud and partner and data center, so that the emissions are least? Similarly, in infrastructure, not just about the device, the scope 1, but about the scope 3 also. So how do you choose your hardware partner? How do you choose your devices in such a way that in the overall cycle, the impact on the environmental is the least? So these are some of the areas that we are working upon when it comes to green software. That's our approach. That's our framework. Now, what we'll do is we'll get into the green AI as an area, as that's the focus point for today. And I'll hand it over to Naveen. Naveen, over to you.
Thank you, Kapil. So yeah, in order to build AI applications, you need to build out an end-to-end process, right? That comprises of data acquisition, data cleansing, building data pipelines, training iteratively, test, and doing deployment. And at each stage, you need to make certain decisions with respect to energy efficiency and carbon emission reduction. So green AI is all about how do you embed energy efficiency and reduce carbon emission as part of your overall AI process, while balancing the trade-offs with your model requirements, such as required accuracy, inference latency, and so on. And the green AI lifecycle starts with understanding the plan for your sustainability requirements, followed by data acquisition, data processing, storage, model building, training, and ultimately customizing and monitoring your AI model. So let's start with the first step. So the first step is basically setting up your sustainability plans for AI design and development, and how you would embed energy efficiency as part of your process. Other choices that impact sustainability includes data foremost. For instance, how much data do you need to train? Can you train with small data sets? And there are research going on leveraging small data and maybe using distributed or federated learning for model development to minimize the overall carbon emission. Now, when it comes to framework, what kind of energy efficient framework you would use? For instance, as per a research study, framework like TensorFlow is 1.4 times faster and 1.7 more energy efficient than PyTorch for building recommender systems, while PyTorch is 2.1 times more energy efficient than TensorFlow for other training models for NLP category. So choosing the right framework based on a requirement becomes important. From a model perspective, can you use a pre-trained model versus building your own? From an environmental standpoint, what kind of infrastructure you should provision? In which region you should run your ML models or train your ML models so your carbon footprint is minimal. For instance, everybody do a lot of experiments, ML experiments. So you can run it on a clean free region provided by the cloud to lower the carbon footprint while training your model. For instance, even simple choices like moving to one region, let's say from Asia East to Europe or North, one region in Google Cloud can cut down the carbon emission by at least 60%. And finally, how do you monitor, track, and report carbon emission and reduce them eventually? So once you have the strategy defined, next step is how do you go about acquiring your data model? So in data acquisition, you typically starts off with what kind of data sources you need to build the model. And this would include external or internal data, different formats, structured, unstructured, satellite data, and so on, based on the requirements. And each format requires building up an energy efficient data pipeline. So the first option is basically to look at availability of pre-processed data. So you don't need to build a pre-processing pipeline. For instance, for satellite data, if you're building, let's say, a carbon sequestration model, you could leverage data available from, let's say, Google Earth Engine or Microsoft Planetary Computing. Another point is how do you want to build out the deduplication logic as part of your data acquisition? So how do you handle duplicates as part of your data acquisition rather than storing the data and then processing it later? Like, for instance, if you're doing sentiment analysis on news headlines, you would typically discard the duplicate news content. And also implementing carbon aware based on the requirements. So you can schedule data acquisition based on the time when you have clean energy available. And data is one of the critical factors that adds to your carbon footprint. And as per a report, data that is lying somewhere in the enterprise constitutes to around 40 to 80%, which is not used for any meaningful insights. So if you store more data, definitely it takes more time to process the data and do computations on it. So having a robust data acquisition strategy is the first step towards greener AI. Moving on to the next slide. So the next step is once you have defined your acquired the data model. And so how do you go about building an energy efficient data pipeline to pre-process, cleansing, and converting it to the required format? For instance, pre-processing and conversion are usually the bulk of the work for building up your ML model. And in this step, we need to look at how you can minimize the compute resources to leverage your carbon footprint. For instance, strategies like using serverless computing for data pipeline to make data pipeline carbon aware and running on regions where the carbon intensity is the lowest. The choice of programming language also plays an important role, or building optimized code also needs to be considered as part of your data pipeline. And going serverless, what basically it means that the required resources are provisioned by the computing platform based on the request and are terminated when the job is over. So it provides effective resource utilization, which basically minimizes your application carbon footprint. Moving on to the next slide. once you have acquired the data, build up the data pipeline, the next stage is how do you store the data? So basically storing comprises of storing the intermediate formats and the actual formats or even the model. And in this strategy, you choose the right energy efficient format for storage. For instance, formats like Parquet for column monitoring database, which can save up to around 80% of storage as compared to a typical CSV file. How do you design the schema and the indexing options also leads to energy efficiency part of your application. And how do you retrieve the data? If you have designed a well-defined schema, your data retrieval also becomes quite easier. For instance, if you're doing, let's say, a stock recommendation based on, let's say, historical and current data, partitioning it, let's say, based on various technical indicators like volume, RSI, and date range would make it easier and more efficient way to retrieve your data during model building and building models on it. Moving on to the next slide. And once you have the data, next stage is around developing and training the model with energy efficiency as one of the key outcomes. And definitely balancing it with your model requirements, such as accuracy and performance. And training, as Kapil mentioned, right, consumes the maximum amount of carbon emissions. So in this stage, you evaluate what energy efficient model should I pick up. For instance, to give you an example, DistilBERT is a minified version of the popular BERT NLP model, which takes in 40% fewer parameters while doing processing of, preserving over around 90 to 95% of the BERT performance. So choosing a model becomes quite important. Now, understanding the impact and accuracy of the carbon emission also plays a critical role. For instance, as Kapil pointed out, right, in a lab experiment, we found out getting an additional 2% accuracy from baseline led to around 15% jump in electricity. So understanding that trade-off and when to stop training, keeping energy efficiency in mind. And the third is around the choice of hardware or virtual machine being used for training also plays an important role, because ultimately the model that you are developing, right, requires, runs on a piece of hardware, and the electricity is basically powering the hardware. So in that scenario, what kind of virtual machine should I use? A lot of cloud providers provides energy efficient virtual machines. You could use TPUs, which is more energy efficient as compared to standard CPU or GPU instances. Moving on to the next slide. And once you are done developing the model, you go about deploying the model. And during this stage, you can apply various optimization techniques like pruning the model to reduce the size, or quantization so that you could reduce the floating point to integers, and then at the end of the layer convert it back to floating point so that it becomes more optimized. And not just it can run on a given piece of hardware, but specifically, let's say if you're running the model, let's say on a resource constrained device, or maybe an IoT device, right? It becomes quite important so that you create optimized model at the source itself, because that model can be deployed, let's say, to millions of devices. So optimization is a key step during model building. And for inferences, also you can use specialized custom chips, which offers high performance, low latency inference. They are offered by various cloud providers. So picking and choosing again which inference model would work for a requirement becomes important. Moving on to the next slide. And once you have the model up and running, you need to look at how to report your carbon emissions of your ML model and integrate it as part of your overall MLOps process to basically track and reduce. And when it comes to measurement, I'll talk about a standard called software carbon intensity, which can be used to measure the carbon emission of an ML application. Moving on to the next slide. Now, as we advance technology sustainability, right, and green software, which includes green AI, which is a relatively new area, we need to look at a community, collective intelligence of organizations, nonprofits, universities, all coming together to advance green software development. And that's where Accenture co-founded the Green Software Foundation to drive adoption of green software through specification, tools, and courses and certification. So if you want to learn more about green software, I encourage everyone to take the free training and certification course that the foundation has recently developed on green software, which talks about some of these principles. And in the foundation, the first problem we looked at is how do you measure the carbon emission of any software application? We go to the next slide. So software carbon intensity specification is probably the first industry-led consensus-based specification that can be applied to any software to measure and reduce its carbon emission. And one of the questions frequently being asked is, let's say, how SCI is different from other specification or standards. So SCI is more action-oriented. It basically talks about reduction and not offsets, which is a key difference. So you're not buying carbon offsets, but trying to look at how can you solve the problem in the first place. And with SCI, you basically get a SCI score. And SCI score can be reduced by 3 key factors. For instance, creating energy efficient applications, using less hardware for same amount of work, or being carbon aware. When I say carbon aware, it means basically utilizing the region and the time where the carbon intensity is lowest, and then running your application. And it's also not about measuring the AI emission, but also principles to reduce it. And from a methodology perspective, what you do is basically you start off with defining the software boundary, like what you plan to measure. It can be a backend application, it can be an ML inference, it can be an ML model. And once you have defined your software boundary, you go about how do you want to scale it. Scaling basically implies, for instance, for a credit card company, it can be transaction per seconds, or for an ML application, it can be APIs or inference per second for an AI model. And once you define the function unit, you go about measurement. It can be a real world measurement of a production server, or it can be lab-based measurement. Then you calculate the SCI score for each component, aggregated, and then you basically get, let's say, a SCI score or carbon equivalent score per API per user. And as part of the foundation, we did SCI calculation for a lot of the large models like GPT-3. So I would encourage everybody to look at this paper, which talks about how can you go about calculating the SCI score for large ML models. And if you look at the SCI equation, is basically simple. It's energy consumed by the underlying hardware, multiplied by the intensity at that point of time, plus the embodied emissions, and dividing it by the functional unit. So embodied emissions also important. So whatever servers that you use, right, has an embodied emission associated with it. So this specification also not just look at the operation emissions, but also from a hardware perspective, right? What are the embodied emission associated with it? Moving on to the next slide. And as part of the foundation, we have this project called Patterns Project, which provides principles to reduce the carbon emission of, in general, any applications, and also include the AI principles, which I talked about on how do you create energy efficient AI applications. The principle which I talked about is listed out there. So please have a look, and you can also contribute towards it. So with this, I like to conclude our presentation. And just the final thought is, as we build machine learning models, AI models, as software practitioners, creating and developing and AI models, I think now we have a role to play in developing energy efficient applications, be it during training or choosing the right hardware, and playing our part towards a greener planet. So thank you all for listening. I'll hand it over back to Udit.
Thanks a lot, Kapil and Naveen. We may have time for one quick question from the audience. Any question? Yeah, so Professor Ganguly, yeah.
Thanks for the talk, and it's very interesting. The works are very interesting. So, one question I have, that you have told that you are ready to sacrifice some sort of accuracy for green, but means if you sacrifice accuracy.
So I can repeat the question for them.
So you have, so one of the aims is, or one of the objective is that you are ready to sacrifice accuracy to attain green, green energy, or to save energy. But that may be, means in some of the applications that may not be very desirable. Means although it looks like 2%, but that may have a great ramification in many cases.
Yeah, no, I think that's a very good question. We keep getting this question. So definitely it's a balance act, right? So not all applications will need, let's say.
So do you have areas where this can be applied and areas where this cannot be applied? This principle can be applied. Do you have some? So
currently, I mean, it all depends on the application, right? Let's say if you're doing maybe a cancer prediction, in that case, accuracy might be more important. But let's say if you're doing general recommendation of products, right? In that case, you might be able to compromise the accuracy. And I think just accuracy, just one part of it. Even if you don't, if you leave the accuracy aside, right? Let's say if you want to build an accurate, I mean, if you want to build an, let's say, an accurate system, but there are other principles which I talked about, right? Which can just mean that running, let's say, on a clean region or a region, right? Where by default, if you choose a right region and right time, you can actually cut down your carbon emissions by 60%. Or maybe the way you develop your deep learning framework or network, right? Which is more optimized. So all those factors which I talked about, right, can also be applied. So it's accuracy, just one part of it, I would say. But the other principles, if you add it, right, from the choice of environment to programming language to what hardware you're using, right, all constitutes towards your carbon footprint. And if you apply the right principles, you can definitely cut down your carbon emission.
Okay, all right. Thanks a lot, Kapil and Naveen. It was a very interesting and intriguing topic. And we look forward to connect to you in person if your schedule permits anytime soon. Thank you. Thanks a lot.
Thank you. Thank you for having us. Thank you.
Thank you. Have a good day.
So now we'll break for coffee and we will be back in the auditorium by 4:45 p.m. for an exciting datathon. Yeah. Yeah, so the finalists of Datathon should be here around 4:40 p.m. so that we can set up presentations, etc. Also, today we have a banquet dinner starting at 7 p.m. in the new guest house area. So please be there.